So it's a pleasure to introduce Jeremy Warner, who actually I first met this year when I was chairing a panel at ESMO, and he was one of the speakers who we invited. Jeremy is the director of the Brown Lifespan Center for Cancer Bioinformatics and Data Science, and an associate professor, technically pending, I guess, at Brown. His clinical focus is malignant hematology, and he received his medical degree from Boston University, and also in a master's in photonics and electrical and computer engineering from UC San Diego. In addition to his focus on malignant hematology, Dr. Warner is a leading expert in the clinical and translational cancer informatics research, including high-dimensional data analysis and visualization, natural language processing of narrative oncology texts, and the creation and implementation of health data standards. Before coming to Brown, Jeremy was at Vanderbilt University Medical Center, where he was an associate professor of medicine and biomedical informatics. And I should also note that he is the deputy director of ASCO's Clinical Cancer Informatics Journal and a founding director of the new Brown University Center for Cancer Bioinformatics and Data Science. So without further ado, you're going to speak to us about using and improving real-world data ecosystem in cancer. Thanks. Look forward to it.
Thank you. Thank you so much for having me. And if anybody wants to come up to Providence, just one stop away on the Acela. So really nice that we're so close here in New England. So I just have a few disclosures first before I get started. So I have some grant funding, some consulting. I do have ownership in hemonc.org LLC, but it has no monetary value unless one of you wants to be an angel investor, and we can talk after the presentation. So what I'm going to talk about here is, why do we need real world data and real world evidence in oncology? And I'm going to focus on electronic health records. There are other sources of real world data, of course, but most of this talk will really focus on the EMR, the EHR. I will spend some time on talking about, in particular, interest in mine, which is standardizing systemic anti-cancer treatment representations. And then I'll spend some time talking about our COVID-19 and Cancer Consortium, which is a bit of a culmination, if you will, of some of these thoughts. So there are some learning objectives here. Hopefully this is a CME. So we'll cover, some aspects of natural language processing and how it can be used to get information out of EHRs, why we need formal representations for complex concepts, such as systemic anti-cancer therapy, and then learning about how these ideas went and propelled the CCC19 registry. Okay, so first of all, probably everybody might be already familiar with these definitions, but I think it's always helpful to go over, what is real world data, what is real world evidence, and it's nebulous a little bit, and depending on where the source you look at, you'll get a different definition. But this is my definition, which is really based on something called the DIKW pyramid. Has anybody heard about this? Heard of the DIKW? Okay, great. So I'll teach you a little bit here. So the idea here is that it's a pyramid where you're climbing levels here from a base of data. The next step is information. The next step is knowledge. The next step is wisdom. You'll note there's 5 levels here. There's a little tiny level at the top, which some people use U for understanding. But basically, the idea is no matter where the data comes from, what it is, whether it's from a randomized control trial or case control, registry, et cetera, the idea is that as you move up this pyramid, you're generating real world evidence, whereas real world data is really that base. On the right here, you see the sort of traditional pyramid of evidence-based medicine. So if you look at this from another dimension, kind of looking from above, when we think about cancer in particular, I think about sort of 3 big aspects of cancer. There's the genotype, the phenotype, and then the environment. And sort of for each of these, you have these layers. So if we think about the data level, for genotype, that's just the sequence, right? Just the somatic tumor sequence. For phenotype, it might be just a histologic type. A cell, what is that? And for environment, it might be pollutant levels. Now, this is data, but it's not really telling you anything, right? So we need to kind of walk up this pyramid. The next level for these three buckets would be for genotype and environment. You might talk about pathogenicity. What does that change mean in terms of, is it a driver mutation? That's sort of the next level information. Cancer behavior on the phenotype side. So is it aggressive? Is it a high grade malignancy, or is it something indolent? Kind of stepping up further for genotype knowledge, the knowledge level is actionability. What can you do with this information? Can you actually prescribe a medication that'll change the outcome for a patient? Phenotype, same, just generally speaking, what are the treatment options? And then in the environment, are there risk modifications that can be taken? And then really getting to that top level wisdom, this is really complicated now. So in phenotype, you're thinking about what are patient values and preferences, and how do those influence what treatment options you might consider. For genotype, what's the tumor going to do once it gets exposed to treatments? How is it going to evolve under treatment pressure? And in environment, you've got issues about social justice and structural racism. So those are all kind of like the ideas of climbing this pyramid. All right, hopefully I've convinced you the difference between data and evidence as we kind of step up. Now, why do we need this real world evidence? Well, clinical trials are wonderful, but they're also expensive, slow to conduct, and they don't always represent the full population at risk. Also, prospective trials collect some, but not all potentially pertinent information. And our space is huge. Oncology, the treatment space in oncology is huge. And then lastly, I think last but not least, is that we've got this enormous data source, which is the electronic medical record. So just a few words about each of these items. So when you think about trials and disparities, this is a paper we just published very recently in this one was earlier this year, and we just published another one in JAMA Oncology looking at prostate cancer. This one looks at immune checkpoint inhibitors across cancers. And basically the take-home message here is that when you look across trials, there is really a lot of disparity in who enrolls in trials. And it can be different by cancer type, but it's pretty consistent across the board. And it's not always underrepresentation. Sometimes it's overrepresentation, as you can see from that bottom row. But essentially the yellow ones, the yellow circles are intersections of, in this case, gender, age, race and ethnicity, and a cancer type, where the enrollment is as you'd expect. If it's green, it's sort of more than you'd expect, and if it's red, it's less than you'd expect. So this gets at generalizability, and there might be statistical ways around this, but essentially, our knowledge from clinical trials is primarily coming from younger white men. Okay, so how about the information that gets left out? So this was amazing. This is the recovery group that really geared up during the early days of the COVID pandemic and found, pragmatic trials that they ran in UK, and they found some really important treatment options for COVID. This is one of their papers. This is probably the most impactful, showing that dexamethasone could help hospitalized patients with COVID. And I've excerpted a table from that paper. Take a minute and look. So what's missing from this table? So this is a table of previous coexisting diseases in the patients who had COVID. Is there something missing from this table? Something that's the topic of this talk. Cancer, right? There's no cancer in this table. They did not collect cancer, or they didn't report it. Well, we actually went and got their case report forms. They didn't record cancer. So here they enrolled tens of thousands of patients in these trials, and they don't know if these patients had cancer or not. And so, I mean, amazing work, but we're missing a key piece of information. And then sort of the last item, that I mentioned before is that this idea that our treatment space is huge, but head-to-head comparisons of important drugs are mostly absent. And I'll just give you one example. So this is the space of PD-1 inhibitors, which have changed obviously changed our fields. From our HEMONC knowledge base, which I'll talk about a bit later, we have 137 trials that have been published using 64 different regimens of various PD-1 inhibitors. This includes ex-US, by the way, if you're like, they're not 13 PD-1 inhibitors. Actually, there are, but many of those are only approved in China. So 83 of those are phase 3 trials. Take home point is one of those 83 actually compared a PD-1 inhibitor to a PD-L1 inhibitor. Kind of, it actually compared to cobimetinib and atezolizumab. And a grand total of 0 of these trials compared one PD-1 inhibitor to another PD-1 inhibitor. So, you know, maybe I'm missing some trials that are ongoing now that have yet to be published, but at this point in time, we don't have any data at all on whether one PD-1 inhibitor is better than another, except for indirect treatment comparisons. So hopefully I've convinced you that we should at least think about using real world data. But they are messy, ambiguous, and unpredictable. So let me talk about some challenges that we have once we start delving into the real world. So first of all, this is real world data from the Medline institution information. Okay, so did you know that there were 21 clinical trial institutions in New Haven? Did you know that? That's amazing, right? Here they are: Smilow Cancer Center, Smilow Cancer Hospital, Smilow Cancer Hospital at Yale, Smilow Cancer Hospital at Yale University, Yale Cancer Center, Yale Cancer Center and Smilow Cancer Hospital, Yale Medical School. All right, I think you get the idea, right? So, I mean, this is real world. I mean, you have to do something. I mean, a computer's not going to know, right? I mean, so if you want to use this data in some way, someone's got to do some work to actually fix this, right? That is a big part of working with real world data. Yale New Haven Hospital, there's the 21st. Okay. Okay, so how about, so that's bibliometrics to some degree. How about treatments? How many tyrosine kinase inhibitors are there? And so this is a little project that a student of mine undertook, where they mapped out how many letters you'd have to switch around or basically misspell so that one tyrosine kinase inhibitor would actually be another one. And so it's fewer letters than you think. You know, these drugs get misspelled all the time in a pretty amazing ways. I see that there's gonna be a little bit of formatting issue with the next slide, but so this is real data from the Vanderbilt University Medical Center. So this is from our text lists of medications. Now you might say, oh, let's just, you know, we've got to be able to get these medications from structured data. That may or may not be true. It depends. We can talk more about that, but these are real misspellings of the drug erlotinib. I think you can tell looking at this that all of these are erlotinib. But again, I mean, if you don't have some sort of system to harmonize all those misspellings, you're not going to know which patient got what drug. So that's, you know, that's a real world issue with real world data. This is work that we did some years ago on staging. So cancer staging is what I call manageable ambiguity. All right. So, and again, and maybe, you know, during sort of discussion, we can talk about the value of structured versus unstructured data. But the idea here is that we would take data from progress notes, from clinical text, all these notes, and figure out if a patient had stage 1, 2, 3, or 4. So just forget ABC. We're just trying to go for the big stages. And, you know, the problem that we knew ahead of time is that these things are going to be recorded variably in different notes by different types of doctors. But, you know, we did a pilot with about 1,000 patients with lung cancer, with over 460,000 clinical documents across them. Now, if you pause for a minute and you think about a chart review, think about how long it would take you to go through 460,000 documents, right? So here's my pitch for natural language processing. You can actually automate this kind of thing and do this kind of work at scale. So cutting to the chase a little bit here. First of all, we found that out of those 964 patients, 99% had some kind of stage phrase in their note, at least one. And we also had a gold standard, which was the tumor registry data. So we were able to compare our system to the subset. You'll notice only 790 out of those 964 had tumor registry data, but we were able to do a comparison, and our system worked really pretty well. The green, basically the matches are in the green, the big numbers. We got some things wrong, but we didn't usually get things really wrong most of the time. So if it was stage 1, we called stage 4. That was a big mistake. Only happened once. This shows actually, so again, 460,000 documents. So what we wanted to say is, do you have to look at all of those, or can you just look at notes that were written right after a patient was diagnosed? If you think of it, some of this inspiration for this project came from the COPI measures. And if any of you have done that work, you'll remember, I believe, and they may have changed, but at one point the COPI measure was stage recorded in one of the first 2 progress notes written after diagnosis. So it kind of makes sense that you would look for stage early on. But if you look at this black line here at the bottom, so just this, are you seeing you don't see the arrow, are you? I don't think you're seeing the arrow. Okay, if you look at the black line towards the bottom, you'll see that if you look at the notes in the first 5 weeks from diagnosis, actually there's a pretty high rate of unknown stage. Like we couldn't determine it. It wasn't until we got to 5 weeks and out that we had enough mentions of stage that we could sort of make that determination. So we saw this kind of inflection point. And so that's another thing just to note when you're working with real world data is that, time matters. Time can matter a lot. And the other thing that really matters is ambiguity. So I mentioned we found stage in 99% of the records. What I didn't mention is that most of those, or 84%, had more than one stage in their records, okay? And some degree of discordance. So one note might say they have stage 1. Another note might say they have stage 2. Actually, when we constructed a network graph on the right here, you see like every possible combination was present. Every possible combination, including more terms that are more generic, like early stage, advanced stage. Everything happened, and on the bottom left here, you can see a histogram of co-occurrences of various stage information. But I do think that really potentially ambiguous. One take-home point from this, though, is that we use a really simple decision rule on what is the actual stage. We just chose the phrase that showed up the most, okay? And that seems to work. So if stage 3 shows up in the notes 100 times and stage 1 shows up twice, chances are it's stage 3, just sort of a practical rule. And it worked. Now, getting back to that, whole idea of, unknown or sort of lack of information and missingness, which is a major issue with real world data. This is another mini project we did looking at colon cancer. And we wanted to say, could you find patients with stage 3 colon cancer? And this was for the OCM project, the oncology care model. So, really important as a metric to know if these patients got appropriate treatment within an appropriate period of time. But again, what we saw here is this sort of crossover at about 7 weeks, at which point, the stage was changing, or it was missing in the records. And it wasn't until about 7 weeks after diagnosis that you get to a kind of steady state where you can definitively say a patient is stage 3, or we don't know the stage. So here's some really interesting work from here, actually from Yale, from the radiation oncology department, where they actually looked at missingness as a variable, if you will. So they took the National Cancer Database, the NCDB data, and they split patients into whether they had complete records or had some missing data from their record. Now, the NCDB is not EHR data, right? But it is based on EHR data. So I would call it a real world data source because it's curated out of EHR data. And the punchline here is that missingness is an independent prognostic factor for survival, which is really an interesting thing to think about, right? And it kind of depends on what kind of cancer you have as well. So they found, for instance, on the left, if you have non-small cell lung cancer, it's the non-metastatic patient who had a real difference in their prognosis if they were missing data. Whereas with prostate cancer, it was the metastatic group that sort of split apart. But either way, I mean, this is, just think about it for a minute while I get my water bottle. It's interesting. Okay, it's certainly not something that we conventionally use as a metric. Certainly not in a clinical trial because it's not an issue, right? Case report forms are complete, but missingness itself can be informative is in real world data. So what I wanted to do now is actually take us down a little different path briefly, which is a brief diversion into the history of medical records. Does anybody know what this is? It's a local Eli Whitney's mill. Okay, so it's kind of cool if you've never been there. It's still there. Doesn't exactly look like this anymore, but you'll see why I'm showing this in a couple of slides. So this is a real thing. Okay, so this is one of my favorite vehicles from the Lane Motor Museum in Nashville, which was Dr. Weiner mentioned. I was there for about a decade. And so this is a real vehicle. They actually have a collection of these. And it makes me think of electronic medical records because it works, right? It actually, this person's actually driving this car. But we don't exactly see propeller driven cars on the roads these days, right? So our EMR, but it works. So EMRs are functional, but are they fit for the purpose that we want to use them for? I think many of us have, some ideas about that. But, when you think about medical records, this is obviously a little bit before the computer. Medical records have been around for almost, 3,500 years in one form or another. But what's interesting to me is that they were primarily used for teaching or didactics until very recently. That was the only purpose of medical records. And then sort of the second purpose that arose, if you will, didn't arise until the 1880s, which is not that long ago if you think about it. And that was for legal purposes, legal defense. And, essentially to have a written record of what happened in case there was a lawsuit around medical malpractice. We'll skip that. And sorry about there's some Mac to PC changes here with the font. So it's a little bit hard to read some of this, but, how about billing? Billing is the major driver, right, of how our medical records look like today. But that only really happened in the 1960s. This is really not long ago. And until, not so long ago, physicians were paid with food and lodging if they were lucky. This is a picture from the Confucian medical system where there's at least some cases where the court physician was basically executed if the emperor did not get better. So that's a pretty harsh payment or penalty, if you will. But what really changed things was the Medicare Act of 1965, which basically established this profile of, quote, usual, customary, and reasonable fees, which drives so much of what we do. And sorry about the font that's messed up here, but there's a quote from the AMA, the American Medical Association, that said that the 1965 Medicare Act was the most deadly challenge ever faced by the medical profession. That's actual quote. It certainly changed things a lot. And then what I'd argue also changed things was really more recent, was in the 90s when the physician fee schedule was introduced, and then something called the Evaluation and Management Guidelines, which I think a lot of us know more than we ever wanted to know about. But those really changed how medical records were written. Notice that I haven't yet used the word electronic, right? Now, what about patient care, which I think all of us want that to be the primary purpose of medical records. This kind of dates back to the 1800s. In some ways, the case records of the Massachusetts General Hospital introduced some ideas like history of presenting illness, past medical history, and so forth. Medical record numbers, the whole idea that you would track a patient by a number, was introduced at the Mayo Clinic in the early 1900s, where they also introduced the chief complaint and the review of systems. And then the American College of Surgeons, this amazing bit of history if you didn't know, in 1918, there was no federal mandate of any. They basically mandated, as a professional organization, they mandated that hospitals had to keep records, including a discharge summary that basically said, was the patient alive or dead at the time they left. And at that time, fewer than 20% of physicians kept any kind of record at all, which is like amazing, right? Now this is tying back to that Eli Whitney. So this is, for those that did take records, this is kind of what they looked like. As these are called case books. I'm not sure where this one is from, but it's basically a handwritten. And what's really interesting about this is that it's physician centered, right? This is a diary, basically. It's not, one patient has one book. This was written as the doctor saw patients. So if you ever wanted to go back and say, okay, Mr. Smith or whoever, like put their case together, good luck. So really the most recent innovation, if you will, in medical records was this one, and from the mid 1960s, which is the problem-oriented medical record, which was conceived as a, quote, medical record that guides and teaches. So kind of back to that idea of didactics in a way. And I'm sure everybody's familiar with this idea of the SOAP note, right? What I like from the paper when Dr. Weed introduced this idea, this is a quote, which I think actually forecasts the EMR, right? So, and it's worth reading it. It can be readily be seen that all narrative data presently in the medical record can be structured, and in the future, all narrative data may be entered through a series of displays, guaranteeing a thoroughness, retrievability, efficiency, and economy important to the scientific analysis of a type of datum that has hitherto been handled in a very unrigorous manner. I think it's an amazing quote. I mean, this is essentially before any electronic medical record, right? But he basically saw it coming. But I think the most important part of this quote is this: to be concluded, right? We're living through the evolution of these electronic medical records. Now this is actually a two-part paper, that's why it says this, but I think, he could have been like, okay, we don't know what's going to happen. It's worth taking a step back and saying so now I'm going to say electronic. What is the electronic health record for? And it's got primary uses and secondary uses. So the primary uses are patient care and delivery, financial, billing. But it's this, when you talk about real world data and real world evidence, that's a secondary use as it's conceived here in this model, which the Institute of Medicine put forward. All right, so moving ahead a little bit. So this is where we were in the mid 2000s. And this is when I was in medical school. At that time, there was issues around funding to, roll out electronic medical records. And what I like on the bottom here is in 2003, the Mass Medical Society did a survey where 89% of physicians wanted EHR data, but 48% refused to use an EHR. So a little bit of a disconnect there. And by 2004, hardly anybody was using medical records. So what changed? Arguably, this is, one of the events that really changed things. Is everybody familiar with Katrina and what happened in New Orleans? Does everybody know why the record? So there's a picture there on the right. Does everybody know why those were in the basement that flooded? They were so heavy that the building literally would have collapsed under the weight of the paper if they'd been up on higher floors. So that's why they had their medical records in the basement. And they were all destroyed, right? They were all just lost. So fast forward a little bit, the HITECH Act in 2009, which Obama signed, this is what really, gave a lot of money for institutions to really start putting in EMRs. But what is interesting is if you look at sort of the adoption curve, and there's a couple, I won't get into the details here. There's a couple of ways of like, what is an EHR basic versus complete and so forth. But you actually see them started. So here's E&M coming out in the mid 90s. Here's Katrina in 2005. There's the HITECH Act. By the time the HITECH Act comes out, actually, we're like well on the adoption curve. And so, definitely it helped things along, but, the process is already starting. And then, so this is already 5 years old, but I think, and sorry, I can't see the text there, but, already by 5 years ago, people were reporting that EHRs were a major driver of burnout. So, it's problematic, but, okay, here's a few other challenges. So and I'm sure everybody who's clinical knows these things already, but carry forward or copy pasting is ubiquitous in medical records. And there's just a ton of redundancy. Here's a paper that basically shows that large portions of any note you particularly look at have been copied forward from other notes. Progress notes in particular, more than half of progress note material is copied forward from previous notes. This is a different study looking at how many progress notes have manually entered text versus copied in any kind, and you can see again, like very few progress notes have fully written text, which you would say is fully original. But so I think it's a legitimate question to say, what are we dealing with here? Is it a giant pile of paper, or is there actually meaning? So this is a little tiny project I did during fellowship, where I basically took one of my patients' charts and I counted up like how many data points are in that chart. And you can see the blue bars are all the structured data elements like billing codes or vital signs or lab values. And then these red bars are the words in the clinical documents. And you see that just drowns out, right, the structured data. So there's a lot of data there, but there's even more than that, right? So in this chart, and this is small these days, right? So this was more than 10 years ago. There was another 277 pages of scanned documents with 69,000 words in them that were basically inaccessible. But and the take-home point here is that this is what it all boils down to. Okay. This is a patient with diffuse large B-cell lymphoma who is in complete remission after getting 6 cycles of R-CHOP. I think that's enough for most research. Okay. Now, how can we boil things down like that? Because that's kind of maybe what we're talking about here. So, and of course, there's more to it, right? But when you think about what's in EMRs or EHRs and what is not, you have to know what you're going to find, right? So let's say you've unlocked this medical record, but it's not necessarily going to have what you want. So here's some basically some big buckets, right? So you're going to find the person's date of birth, no problem, right? But you're not going to find probably where they were born, the circumstances of their birth, were there complications. Very unlikely, because they will have, they won't have lived their whole system with their life within the electronic era, and they won't have all that data. You might find their biologic sex, no problem, but are you going to find their gender orientation and sexual identity? You'll find race, ethnicity, but are you going to find other social determinants of health? You'll find the medications that they are prescribed, but will you find what they actually took, the medications that they took, and the regimens? And we're going to get into that next. You'll find laboratory tests, but you won't necessarily find images, and so forth. So kind of, as moving forward, thinking about what, the low-hanging fruit, it's the cancer type, it's easy. Like, we don't need to create a new system to get cancer type. You can get that from billing codes, registry data. The treatments are hard, like R-CHOP times 6, that's hard. Determining that the patient's in a complete remission, that's really hard. So what I go for the middle. I'm gonna go for the middle ground, right? I'm gonna tackle the thing in the middle. So now I'm gonna switch gears here for a bit and talk about our work on standardizing systemic anti-cancer treatment. Before I get into that, if you've not seen this XKCD cartoon, it's a classic. And this is a challenge, right? Whenever you decide to create a new standard, are you actually just creating more complexity or not? Hopefully we're not. Well, what we did in this space, there really weren't 14 existing standards. There were none. And so, as everybody here knows, I can skip past this slide, chemotherapy regimens are complicated and given in cyclic fashion, combinations. This was the standard when we got started on our work. This is, one example of these things called cancer chemotherapy handbooks, kind of recipe books, physical books, right, with some details here, but maybe not enough. Here's another example from 2005, which, if you kind of look in detail about what's there, there's a lot of optionality here. Some of the references Here's a little excerpt from the adenocarcinoma of unknown primary section, but the references are to non-small cell lung cancer. So there's sort of a mismatch there in the evidence base. So what we did is we really basically tried to collect all this information and put it into a computable format, which is our hemonc.org website and the ontology that comes from it. So hemonc.org is a website with a goal to collect all standard of care systemic anti-cancer treatment. That's the goal. It's a big goal. And the website's grown over more than a decade now. We have almost 1,000 primary content pages, over 7,000 references, and a large editorial board, actually members of which are from Yale, and many page views, so 1.4 million page views last year. We do get visitors from all over the world. We're primarily US based. I always like to throw in that we've had one visitor from North Korea. I don't know who it is, but I don't think I want to know. So what can we do with this website? So what we did over time, over the past 11 years, is create a structure such that we could actually take the content and develop a formal model. And so this is the model, or this is part of the model. And I don't have time right now, obviously, to kind of go through all these details, but it's somewhat complex and large. We have over 100,000 concepts and 300,000 ways in which those are interrelated in the latest version. This is basically, this is showing, I don't have time to actually show the website. This is a screenshot from the website showing basically that each regimen on the website is in such a way that we can take all those pieces and put them into the data model. And then we can start to do cool things with real world data. So here's a project that we did with some folks in South Korea who basically had access to essentially medication level database. And remember I mentioned, way back when that we might get medications, but to actually understand regimens, we have to do something extra. And so what they did is they applied our model and they mapped medications to regimens, and they were able to look basically over a decade of time, 2008 to 18. And you can see here that, the changing pattern of care in that country. So you see that, for example, bevacizumab wasn't used really until 2014, and then it started getting popular. And by the year 2018, it's, FOLFOX and bevacizumab is making up a good chunk of the treatment regimens, whereas something like fluorouracil monotherapy essentially disappears off the scene by the time you get there. This is much more recent, so that's from a couple of years ago. Now we're working with folks at the University of California system, have a really cool combined database across all the UCs, and California is kind of a country unto itself once you start putting all this data together. This is just from UCSF. And again, we're taking medication exposure data, including timestamps, and we're mapping that to regimens. And you see that at least nowadays, FOLFIRINOX is the most popular regimen there. And so that alone is an interesting thing, right? You also see some funny things, right? Like, so I didn't know Leuprolide was a treatment for pancreatic cancer. Did you? Is it? No, right? No, but these are real patients, right? And they actually have second malignancies. So these are people who also have prostate cancer, and they're also getting Leuprolide. So you kind of have to, it's not enough to get that data out. You got to apply knowledge, right? You've got to determine, what am I looking at? Does it make sense? Is it relevant? And so that's why we're seeing things like that. So here's another that gives you a taste of what we can look at. So this is looking at FOLFIRINOX and then looking at cycle by cycle what's happening. So one of my long-term interests, as well as Dr. Zach here, is to understand treatment delays, dose reductions, removals of medications from a regimen, dropping a drug. And this starts to get at that. And you can kind of see, each of those bars represents cycle to cycle to cycle. You see people dropping out, right? And then you can actually see why. And you can see on the top here, these bands at the top are showing, these are folks. Yeah, I don't think do you have a pointer or something? Oh, actually, let me see if this will, yeah. So you see these bands coming across. Those are basically patients that are progressing and going on to a second line treatment. What's not shown here, just to spare you a little bit on the visual side, are patients who are stopping therapy and essentially transitioning to hospice or some sort of end of life care. And that's this big bar here. And then some patients, these little ones, they're going to a de-escalated regimen. So they're dropping the irinotecan or the oxaliplatin. And so you can really start to see these patterns of care in the real world data. So, okay. So this is my little advertisement for HEMONC. It's available to you. You can download the whole thing and mess around with it if you're an academic or non-commercial user. Just Google HEMONC Dataverse and you'll find it. Or you can use these links. It's also available through something called the Odyssey Athena vocabulary. And yeah, I mean, we want more users. There's, I think, a lot more that can be done with it. So along comes a pandemic, right? So now I want to spend the last little bit here talking about the COVID-19 and Cancer Consortium, which Yale's a member. This is our mission statement, which has been the same since we were created in March 2020. Which is our goal is to collect and disseminate prospective, granular, uniformly organized information on people with cancer who are diagnosed with COVID-19 at scale and as rapidly as possible. But what I want to talk about here for a minute is sort of what I call the ancillary goals of CCC19, or the unwritten goals. So one of those was, can we build a consortium? Can we build an airplane while also flying it? Can we do it? That was the question. Convening a group of stakeholders was really a goal, including patients, really engaging patients. And then pertinent to the talk today, can we demonstrate the additive value of real world data elements that are not easily obtained from structured EMR data? We knew that there were other efforts kind of getting rolling that were based on what was in that structured data. If you remember, that's the tiny little blue bars, right, on the graph I showed you. So we wanted to, get more than that. So this is back in Rhode Island. All right, showed you Eli Whitney earlier. This is this is Slater Mill in Pawtucket, which I think I pronounced correctly, but I'm getting my New England chops. And what's interesting to me about this story is that he earned this name, Samuel Traitor Slater. And the reason he was branded as a traitor is that he was accused of stealing the ideas for industrialization from England, where he was born and grew up, and then replicating it in America. So this is really the beginning of the American Industrial Revolution. But what's interesting about that is that he didn't exactly steal the ideas, like he didn't steal blueprints or things like that. He just memorized them and brought the knowledge with him. So it's, that's what he did. So I think that that's great, actually. And so, when we think about CCC19, and I certainly don't have time to go through all this, but we have many inspirations. The HEMONC, what I just spoke about, is one of them, but in all the domains of CCC19, we are borrowing best ideas, modifying sometimes, and putting together this consortium. And this is just sort of a list of that. The other thing I wanted to say about the CCC19 work and just research in general is that sponsors are critical. In Samuel Slater's case, he had a sponsor named Moses Brown who basically fronted him the money to build those mills. And our sponsor is Julie Clem at NCI, who didn't front us any money, but was very supportive and helped us kind of surface and socialize our ideas. So this is our data schema. And what I want to emphasize here related to this talk is that everything in red is not available in structured data. So as we sort of built this up, some of these things you can collect, in many different ways, but the red items, and you'll see in a few slides that those turn out to be critical. Things like ECOG performance status, things like toxicity of cancer treatment, pneumonitis, items like that we really wanted to zero in on. I'm going to skip this slide. I'm going to skip this. And I'm going to just say that we've done really pretty well on capturing what I would call elusive variables. So these are kind of the things that they're in the EMR, but they're in that unstructured lake of data. But we got a lot of them. So cancer status, is the patient getting better, getting worse, or staying the same as before, a stable disease? We have that in over 95% of the patients. Even smoking status is hard to get, right? We have that. Did COVID affect the patient's treatment plans? That's not going to be in structured data necessarily. We have over 90% on that. The ECOG, which is a notoriously difficult thing to get, and all the various efforts such as Flatiron and so forth have had challenges, and CancerLink have had challenges with this. We have ECOG data on 88%, although that includes patients who just didn't have an ECOG recorded, but that knowledge of no ECOG is still knowledge, right? And getting to our results, again, just focus on the red. And what we found is that these elusive factors are really important. And so this is unadjusted, just kind of descriptive. If you had progressing cancer at baseline and you get COVID, your 30-day mortality is 26%. And if you had an ECOG of 2 or higher, your mortality is extremely high. We also found that immunosuppression, which is a somewhat nebulous definition, and we have our definition here, which is complex, which includes a lot of things you can't easily get out of structured data. So this is sort of the real world data, is a huge driver of mortality. And if you look at on the right, the yellow table, basically those are the patients who are immunosuppressed at baseline. And across the board, even younger patients have substantial mortality in our data set. Furthermore, if you add on top of that active cancer, so are they immunosuppressed and they have active cancer? Again, we have our definition for that. First of all, if you're not immunosuppressed and you have inactive cancer, in our data at least, you have a 0 chance of dying in the 30 days. Whereas if you're older, immunosuppressed, your chance goes all the way up to 30%. So really a huge spread here based on these data. And then if we start to look at multivariable or adjusted analyses, again, we see that these factors like ECOG or cancer status are highly associated with outcome, both mortality as well as severity, which means hospitalization, intubation, and so forth. We saw this as well more recently when we looked at vaccinated patients, so patients who are getting breakthrough COVID-19 after vaccine. Again, we saw things like cancer status really, being a huge adjusted odds ratio there of 6. If you had an active and progressing cancer of dying in 30 days. So I could talk about COVID, CCC19 itself for an hour, but I'm going to pause. And so I just want to share some parting thoughts. So first of all, I think I'm a believer here that real world data has a great potential to yield real world evidence if we approach it with an understanding about the completeness issues, the accuracy issues, and we anticipate them, and we come up with either ways to adjust for them or avoid certain data, certain variables in the first place. We need, yes, we need automated methods, right? Like it wouldn't be great if NLP and a computer could do everything, but in reality, a lot of real world data and real world evidence depends on human curators going into EHRs, pulling out that data. And to do that, we need rigorous approaches. We have a paper published earlier this year describing the approach we used in AACR Genie. I encourage you to check that out. It basically gets into, you need directives, you need 2 people to independently curate the same record at a certain rate, so you can see if there's comparability between their results, and so forth. If there's widespread adoption of standards such as M-code, HEMOC, OMOP, and so forth, that will increase the usefulness of structured data markedly. I think NLP is having a moment. If you pick up the newspaper nowadays, you're going to see a paper on, you're going to see an article on ChatGPT, for example, which is generative NLP, but sort of the other side of NLP. And then, really important though, and I didn't get to touch on this at all, except for the very beginning when I alluded to disparities and bias. There's a lot of concern that working with real world data might actually make biases worse that are already present in that data. So we need new approaches to deal with that issue. Just have some acknowledgements here. So this 2 slides here. So this is my first acknowledgement slide. I acknowledge the HEMOC.org editorial board, others that have worked on it, our funding, and Dali, which is the creator of some of those graphics you saw. And here's our acknowledgement for the CCC19, which is a huge endeavor that has more than 600 active investigators at this point. And with that, I will pause for questions.
So I'll start. And can you see the ones that are online or not?
I do see, yes.
Okay,
Yes, I see.
so we'll get to that in a second. So I don't for a second dispute the value of real world data in terms of being able to answer questions. But I'm struck by the fact that we have these 2 extremes. We have randomized controlled trials where we spend a fortune to collect every last bit of data. And, they cost $15,000 per patient or more. And we get lots of useless data as part of it. And then we say, well, we can't get everything from randomized controlled trials. So then we go to real world data where everything's pretty messy and you have to make all these assumptions and clean up the data. And the question is there a role for much simpler randomized trials done as part of standard practice?
I mean, sure. Yeah. I mean, I think the recovery trial, I mean, that they showed that you can do these huge pragmatic trials in tens of thousands of patients they didn't spend a lot of money. I mean, they used off the shelf drugs, right? Dexamethasone, things, some of the drugs we won't say the words, but and things like oxygen, right? But when you get into the the expensive drugs that are not yet FDA approved, I think that's a whole nother area. But I think the FDA has got to lead the way in some ways here, because and I didn't get to talk about this, but there's a high profile rejection of real world data within the last month or two that there was an attempt to get something approved based on some real world data. And I think they rightly looked at that and they said that this particular set of data is not trustworthy and we're not going to go for it. But I don't think that should shut down the whole endeavor. I think that we need guidance from them and about what components should and should not be, collected routinely. I think that might simplify things a lot.
And has there been an attempt to put together criteria that would allow you to say that this set of real world data is adequate to draw conclusions from? In terms of how much it has to be cleaned up, how large the sample size has to be, on and on.
I think it's such an interesting question, and I'm not aware of anything at this moment, but I do, we are, there's this great bias that I just learned about called the informed presence bias, which I kind of knew. I knew it, but not by those words. But that basically means that patients who spend a lot of time in the clinic or the medical system have a lot of data, right? Whereas those that don't. And it's actually an incredibly important source of bias so if a patient doesn't spend enough time to get enough data generated, that's something we should know. That's something we need to know, right? But that's almost, that kind of, descriptor is almost never available in any real world data study, to my knowledge. So Yeah.
Before we get to the online questions,
Yeah. Yeah, so the question is, it seems to be the case that that patients with the pre-existing cancer are having worse outcomes during the COVID era than before. And why might that be? Well, I can say from our consortium, now we only look at patients who had COVID, so that's a subset, right? Well, as time goes on, it's going to be everybody maybe, but what we do see is that at least in our registry, 40% of patients have their treatment altered in some way. And usually that's a delay, but sometimes they can't get the same treatment that they were getting before. A surgery gets canceled, et cetera, et cetera. And we know from, previous work, obviously, that treatment delays don't usually ever work out very well. So we haven't yet systematically evaluated that, but we have, now several thousands of those patients. So we're going to be looking at that probably in the upcoming year. As far as other patients, well, I mean, and there were a lot of practice changes, right? Especially in China, I think, but also with sort of substituting oral medications whenever possible, even if they were sort of known to be inferior or not, not quite as good, so that patients didn't have to come into the clinic. So that's been presented on in some settings. But I think, well, we think that those substitutions are generally okay. I know that a lot of people went on neoadjuvant hormone therapy instead of going direct to surgery for early stage breast cancer, and so that they could push this, during periods of time when elective, quote unquote, elective surgeries were shut down. So all those things probably add up, right? But there's absolutely a factor of psychology in patients being afraid to come into the clinic, and potentially again skipping a treatment, or so I think the answer to your question is that it's quite complex, but I think we need to understand it better. And of course, new diagnoses coming in, which we're starting to get that information. There's clearly a stage migration and to later stage, more advanced, more metastatic disease because of delays in screening and so forth. So I think we're going to face a challenging decade, and I think Ned Sharpless forecast that at the very beginning of the pandemic. I think in the first month or two, he wrote a paper in Nature or Science, I think, modeling out what that might look like, and that's probably gonna come true, but hopefully COVID ends really soon, right? So, yeah. Yeah, so we're over time, and I think, I mean, there's many strategies to try to mitigate, but you can't eliminate bias, right? So you can understand it, you can try to mitigate it. There's there's matching strategies to, if you're doing sort of a case and control style approach, where you try to make the controls as similar to the cases, and everything but the exposure. So and some of those have been around for decades. Some of those are kind of emerging at this point. But I don't think we can forget that there's bias in prospective trials as well, right? So I mean, I think either side of the coin. Yeah, it's just one more thing, and it's not the only. I mean, there's ascertainment, but I mean, there's a lot of biases, right? One thing we've worked on with our consortium is developing standardized language around limitations, which I think is critical. Because, I mean, the data are the data, use the plural, right? But the way it's presented really does influence the reader, right? So that's something we're thinking about, and might have some thought pieces or something coming out about how to handle that.